Yes, in this class, we will discuss about another concept type of stress called shear stress and also the corresponding strain called as shear strain. So, we have learned about the normal stresses or direct stresses. So, if the stress acts perpendicular to the area, then it is called as normal stress or direct stress. There are two types in that, tensile stress and compressive stress. So, till now we have discussed some problems about those things, tensile and compressive stress. Now, the next type of stress is called as shear stress. To understand what is shear stress, let us consider a block like this, which has got, of course, I will take a three-dimensional one only, like this, and I am going to take one side, one edge of the block is fixed at the bottom AB, and the other edge I have taken free. So, I am going to apply a force like this, see here. So, this is your CD. So, on this CD face area, this area, I am going to apply a force parallel to the area. So, please note that if you apply perpendicular to the area, it is normal stress, tension or compression. But whereas if you apply parallel to the area, that is called as shear force or tangential force. So, F is called as the shear force or tangential force, and the corresponding stress that is going to develop due to that shear force is called as shear stress, which is denoted by tau here. Tau, Greek letter tau. So, normal stress is sigma, shear stress is tau. So, tau is the shear stress which is given by whatever shear force is acting divided by the area over which that force is acting. So, area here is called as shear area, A. So, F by A, it is called as tau. So, once again the units is same, MPa, Newton per mm square, because force will be in newtons, area will be in millimeter square, Newton per mm square. Sigma also is in Newton per mm square, tau is also in Newton per mm square. Okay. Now, due to that stress that is going to be induced in the material, there develops strain also. Wherever there is stress, there will be strain, because the direct stress is directly proportional to strain. So, that strain here is called as shear strain. The other word for shear strain is angular deformation. In this diagram, so due to the effect of this F, since it is free here at C, it gets shifted to C dash. There will be a shift there. Lateral shift will be there from point C to C dash, because it is acting like this. Suppose if F acts like this, the sheet is shifted towards left, C dash. Here I have taken towards right. So therefore, this value, whatever it has shifted, that I have taken as delta. It is called as lateral deflection also. Delta is called as lateral deflection. Lateral deflection. So that lateral deflection, of course, here I have taken same at both the ends C and D. So this is also delta, this is also delta. If I take this height as h, then if you join this AC dash, you get a right angle triangle here. So in that right angle triangle, I will take this small angle. See, this angle is very small. This gamma is very small. This gamma, since it is very small, this deformation is very small within elastic limits. So this gamma can be equated to tan gamma. In trigonometry, you know that if theta is very small, sin theta is equal to theta and tan theta is equal to theta and cos theta is 1, where theta is in radians. Similarly here, gamma if I take in radians, very 1 degree, equal to 1 degree. 1 degree means it is nothing but 1 divided by 180 radians, very small value. So in that case, gamma can be written as tan gamma. Tan gamma in this triangle, it is CC dash, opposite side by adjacent side, CC dash by AC. So that is delta divided by H. Delta divided by H. So this delta divided by H, it has got no units because delta is also in mm, H is also in mm. The strain is having no units. There are no units for shear strain. So shear strain is also defined as angular deformation, whereas your linear strain is nothing but linear deformation. This is angular deformation. Now we are going, just like Young's modulus or modulus of elasticity, we are going to define one more elastic constant within elastic limits, that is called as modulus of rigidity, or short form is rigidity modulus. This rigidity modulus is denoted by G, or in some books they use C also for rigidity modulus, which is nothing but the ratio of shear stress to shear strain within elastic limits. So whatever definition expressions we are giving, Young's modulus or rigidity modulus or stress or strain, they are all within elastic limits. That you have to keep it in mind. And the units for modulus of rigidity is same as that of Young's modulus, Newton per mm square. Because here tau is Newton per mm square, gamma no units, therefore G also is in Newton per mm square. Now this is about the concept of shear stress, shear strain and modulus of rigidity. Now we have to know about one more thing called pure shear or simple shear. What do you mean by pure shear? So if the material is subjected to only shear force, there is no normal force, there is no tension force, there is no compression force, there is no bending force. If it is subjected to only shear force, then it is called as pure shear or simple shear. Here I have taken a diagram here. ABCD is a block, so which has some areas like this. Thickness. Here thickness I have taken 1. It is of unit thickness, and height, of course, I have taken both sides, width and height. It's a square block, so you can both take the height as well as width as h. So in that case, if you take the shear area remains same on all the cases. So it is h into 1, because it becomes a rectangle. The area becomes a rectangle. H into 1, that is h only. Now we know that stress into area gives the value of force, because stress is force divided by area. Stress into area gives the value of force. So here shear stress, which is equal to tau. Tau I have taken like this. Area is the shear area, this hatchet portion, that is h, that is equal to your F. So wherever this tau acts in the same direction, that F also will act. Please note that in whatever direction F acts, in the same direction tau also will act, and vice versa. Now here, when you take a force or a stress in this direction, naturally for equilibrium on the other side, on the opposite side, the stress should develop in the opposite direction. See here I have taken towards right here. Tau is towards right here. Bottom I have taken towards left, because these two is in equilibrium. So one force is acting towards right, another force is acting towards left, equal in magnitude, opposite direction, parallel. Therefore, a resultant force is 0. Of course, it will have a moment. So due to this, it develops a moment like this. Clockwise couple, it develops like this. So of course, F into, so that moment is nothing but F into h, because the distance between these two is h. Similarly, if I take another two forces in these two directions, for example, I have taken here like this downward tau, here upward tau I have taken. Tau means it is F only. In the same direction, shear force F will be acting. Here these two will give, you can see, anti-clockwise. Anti-clockwise couple it will give. So F into h only. Now one is giving clockwise, another is giving anti-clockwise. So therefore they will get cancelled each other. Sigma m is equal to 0 is satisfied. Equilibrium equation is satisfied there also. Therefore moment of the force F about any of the points in the plane, it becomes 0. That means it is not subjected to any rotation at all. There is no moment at all. In such a state of stress is called as simple shear stress or pure shear stress. So very important. So in pure shear stress, the element is subjected to only shear force, only shear stress will be developed, no tensile stress, no compressive stress, no bending stress. This is the concept. Now we have to define one more elastic constant called Poisson's ratio, which is denoted by mu. So mu, Greek letter words, Greek letter mu. All are Greek letters, sigma, mu, tau, gamma, everything is Greek letter. Or some books they use 1 by m. 1 by, because it is a fraction, it's a decimal, it can be expressed as a whole number also. So 1 by m. For example, m is equal to 4 means it becomes 0.25. 1 by 4 is 0.25. M is equal to 3 means 1 by 3 means 0.33. So like that mu value is expressed. How it is defined? Mu is defined as the ratio of lateral strain to linear strain. Very, very important. Of course, this is also within elastic limits. So all these definitions are defined within elastic limits. So lateral strain to linear strain. So lateral, you have to understand these two words. So to understand lateral linear strain, I have drawn a diagram here. It's a cylindrical rod. That means cross section is circular. So it is subjected to tension force P on either side. So initial length I have taken L. So since it is subject to tension force, there is elongation. Length will increase. That new length I have taken L plus delta L. Initial diameter I have taken D. Then after elongation I have taken it as d minus delta d because it has reduced. That's why I have used this minus sign. Now here delta L is the change in length. This change in length will be increase in length if it is a tension force. It is decrease in length if it is a compression force. So P is compression, it is decrease in length. Similarly, delta T, it is a change in diameter, it is reverse. It is decrease in diameter if it is tension force, it is increase in diameter if it is a compression force. Now, if you take the ratio of lateral strain to linear strain, lateral strain means perpendicular direction. See here, I have written here. This is linear, along the length. If you measure x-axis, if you measure this is x-axis, this is y-axis, like that you can treat perpendicular to each other. So along the length, if you measure the strain, that is called as linear strain. So linear strain is nothing but delta L by L. So delta L by L is the linear strain, epsilon linear. Whereas along y direction, the diameter will be there. So diameter is there in the y-axis. See, this is y-axis, this is x-axis. And of course, z direction also, it is diameter only. In this direction also, it is diameter only. In the case of the circular rod, x-axis length, y and z axis diameters. So if you take linear strain, it is delta L by L. Lateral strain in y direction or in z direction, it is delta d by d. Change in diameter divided by initial diameter. So that is why this epsilon lateral divided by epsilon linear, this is called as Poisson's ratio. Actually, it will be less than 1. Maximum value of mu is 0.5. We can prove that. Anyway, so here delta d by d is the lateral strain, delta L by L is the linear strain. The ratio of these two is called as a Poisson's ratio, which is denoted by mu or 1 by m. Here I have shown how the strains will develop. So epsilon x is the strain in x direction, corresponding stress is sigma x. Epsilon y is the strain in y direction, corresponding stress is sigma y. Epsilon z is the strain in z direction, corresponding stress is sigma z. And normally, so these two will be at right angles to each other. Normal stress is always perpendicular to the cross section area. You can observe here, this is the area. So perpendicular to it, it is normal stress. So normal stress is sigma. So this normal stress is normally, it is tension or compression. Either it is tension or compression, whereas at right angles to it, it is shear stress, which is nothing but tau. So tau, depending on the sign convention, you can take it as positive or negative. Let me discuss later. Anyway, perpendicular to sigma, tau will be there. Perpendicular to sigma, tau will be there. That you have to understand. And in this direction also, you will be having tau only. Z direction also will be having tau. So x, y, z. So if you take any area perpendicular to the area, normal stress will be there, one value, whereas in other two directions, y and z directions, you will be having the shear stress. So totally it is a three-dimensional stress system. So this is called as 3D stress system. So if the stress is acting in only one direction, it is uniaxial stress. If the stress is acting in two directions, sigma x and sigma y, it is biaxial stress. If the stress is acting in three directions, it is called as triaxial test, where stress sigma x, sigma y, sigma z, all the three will be there. So in that. So if only tension or compression force is acting, it is uniaxial. If in addition to tension, if you want to calculate shear stress in one direction, then it is biaxial. In addition to tensile stress, if you want to calculate shear stress in other two mutually perpendicular directions, then it is triaxial stress. So like that, we have to distinguish between uniaxial, biaxial and triaxial stress system. Thank you.